Today we're going to continue our study on polynomial functions. In particular, we're going to talk about some terminology that's used, in particular when it comes to talking about the zeros of a function. So let's say you have a polynomial function f of x. If r is a real number that satisfies any of the following statements, then r satisfies all the statements. Or in other words, a lot of this terminology, they represent different things, but they really all refer to the same concept within the polynomial. So first, we say that r is a zero of the function f. That means that when you plug in the value of r, it gives you 0 for your y value, for your function. So we would say r is a 0. Another way to think about that is to say that r is an x-intercept of the graph of the function of f. So this is where it crosses the x-axis, because where it crosses the x-axis is exactly where your y value, your function f, is equal to 0. We would also say that x equals r is a solution or a root of the equation f of x equals 0. So for your polynomial, if it's set equal to 0 and you're trying to solve for it, you're really trying to solve for the x-intercepts. So you're really finding a solution, and you can say x equals r is a solution of that equation. Lastly, x minus r is a factor of the polynomial f of x. Now this one's slightly different because now you have a minus in front of the r, so when you write it in factored form, it's going to be the opposite sign. So if, for example, r is equal to 2, then your factor would be x minus 2. Alright, and then one last thing to note is that there is a one-to-one correspondence between the linear factors of f of x that have real coefficients and the x-intercepts of the graph of f. So really what this is saying is when you're looking at algebraically and looking at the linear factors, this corresponds to the x-intercepts on the graph of f. So take a look at this example. F of x equals 15x cubed minus x squared minus 114x plus 72. Find the following. Alright, so the x-intercepts of the graph of f, we are going to have to do this using a graphing calculator. So to find the x-intercepts, we are going to go ahead and graph it, and we are going to find the zeros. So here's the graphing calculator. I'm going to plug this into my y equals. So 15x cubed minus x squared minus 114x plus 72. You hit graph. And now while it's difficult to see the shape of the graph, we can definitely see where it crosses the x-axis. If you want a better picture of what this looks like, it looks like we want to show more of our y-axis. So if you want to get a better picture of the graph, I'm going to change the window. You can see we have a better picture of this graph, maybe still not ideal because you can't really see exactly what's happening with the curve. But again, it's not necessary to change it, but if it's helpful for you to see, you can absolutely continue to change the window. So that gives you a little bit of a better picture of what this looks like. So now let's go ahead and find the zeros. So we want to use the calculate function here, which is the second and then trace buttons. And you want to scroll down to 0. Now the calculator needs you to tell it which 0 you want it to find. So it's going to ask for a left boundary and then a right boundary, and then depending on your calculator version, it may ask whether or not you want it to guess which one you're looking for. I'm going to start by trying to find the one on the far left. So we just want to make sure that we are on the left of this 0. Hit enter. It'll ask for a right boundary. Hit enter. It'll ask you whether or not you want it to guess which 0 you're asking for. I'm going to hit enter one more time. and it finds that the 0 here is at -3. All right, we're going to do the same thing with the other zeros. It looks like our next 0 is at 2/3. And one last 0 to find. It looks like that 0 is at 2.4. So we found 3 zeros, -3, 2/3, and 2.4. So those are our x-intercepts, which is interchangeable with the term the zeros. Now if you have that polynomial 15x cubed minus x squared minus 114x plus 72 set equal to 0, we call these the solutions to that equation. And lastly, the linear factors. This is where you want to write this in terms of x, right? So each factor will have x in it, and you want to make sure that you have the opposite sign. It's always x minus the factor. So x minus -3, x minus 2/3, x minus 2.4. So this is x plus 3, x minus 2/3, and x minus 2.4. Those are the linear factors of this polynomial. And now for part B, you need to factor the polynomial using the factor theorem. So the factor theorem, really, you just know that since we have those linear factors, that all of those are, so the factor theorem is just saying, well, if you know that certain things are factors, you can just plug them in and you will get 0 for the remainder. So in this case, we actually already have the 3 factors, and what you can do is, well, you look at what you have here, and you look at the degree of the polynomial that you're given, which is 15x cubed. Since this is x cubed, and you actually already found all 3 of the linear factors, all you have to account for is any sort of coefficient that might not be there. In this case, the coefficient that is missing, if you look at the first term there, x cubed. If you were to take the 3 linear factors that we have right now and you were to multiply it out, our x cubed term would have a coefficient of 1. But since we've already found all of the linear factors, then we just need to deal with the coefficient, and so we just need to multiply this by 15, and that is going to be our polynomial. Alright, example 2. Find a polynomial with leading coefficient 1 in degree 4, which has 1, 2, 3, and -5 as zeros. Alright, so we just need to first start off by writing out the linear factors. So that would be x minus 1, x minus 2, x minus 3, and x plus 5. Now the leading coefficient is 1, so we don't need to put any number out in front like we did in the last example. It has degree 4. We found all 4 linear factors already, so we are all set. That is the polynomial. Find a polynomial of degree 3 with leading coefficient 2, which has 3 and -4 as zeros. Alright, if 3 and -4 are zeros, then our linear factors would be x minus 3 and x plus 4. And it says we have a degree 3 polynomial. Now here we only have 2. Now, since we don't know what any of the other zeros are, and we'll assume that all the zeros are listed already here, what that means is that one of these must be degree 2. Now, since we're not told which one is degree 2, it really doesn't matter which one you make raised to the second power. So let's say I make x minus 3 raised to the second power, and we'll say the leading coefficient is 2, so we just put a 2 out in front. And that's it. Example 3. The graph below is a polynomial function f of x of degree 4 whose leading coefficient is 1, but the graph is not drawn to scale. Use the factor theorem to find the polynomial. Okay, so because you know where the zeros are, you can determine what the linear factors are. So we have zeros at -2, -1, 1, and 2. So that means the linear factors will be x plus 2, x plus 1, x minus 1, and x minus 2. It tells you that the leading coefficient is 1, so we don't have to worry about dealing with the coefficient out in front, and so that is our answer. Now, as you've noticed as we've gone through these examples, one common thing is that the degree of the polynomial tells us how many zeros we have. So a polynomial of degree n has at most n distinct real zeros. Now it definitely has n zeros, but n distinct real zeros meaning they are different from each other. So in the other example where we raised 1 to the second power, that one had 2 distinct real zeros even though the degree of the polynomial was 3. So at most, it has n distinct real zeros. So it could have had 3 at most, but it only had 2, which is fine. So in example 4, state the maximum number of distinct real zeros of f. So f of x is given to you here. And since this is a degree 4 polynomial, that means the maximum number of distinct real zeros of f is 4. That's it. Now that could mean that it only has 3 distinct real zeros, but at most it can only have 4. It definitely has 4 zeros, but notice that the word distinct is in there. Last example. Find a number k satisfying the given condition. X minus 3 is a factor of this given polynomial. There's a k in there. Now, how would you figure out what value k has to be in order for this to work? Well, let's use the remainder theorem. The remainder theorem says, well, if x minus 3 is a factor, if you were to plug 3 in using the remainder theorem, we know because this is a factor, we should get a remainder of 0. So let's go ahead and plug 3 in. So if x minus 3 is a factor, then f of 3 has to equal 0. So this entire thing has to equal 0 when we plug 3 in for x. So 3 to the 4th minus 5 times 3 to the 3rd minus k times 3 squared plus 18 times 3 plus 18 equals 0. Let's simplify that as much as we can. So we have 81 minus 135 minus 9k plus 54 plus 18 equals 0. Let's move all those constant terms over to the other side and combine them. So we end up with negative 18 on the right. Divide both sides by negative 9, and you get that k is equal to 2. So in order for this polynomial to equal 0 when x is equal to 3, k must be equal to 2.